好，so hello everyone. Welcome to the Digital Futures Lecture Series, for the International PhD Program of Tongji University. So today is a really great honor. We invite Professor Mike Xie to be here with us, give a lecture. So before we start, 姚老师您来开场吗？还是我来？
你来，我在机场不方便。
哦，好，So before we start, please allow me on behalf of Professor Philip Yuan to introduce Professor Mike Xie, our guest lecturer today. So Mike Xie is an Australian laureate fellow and a distinguished professor of RMIT University, where he directs the Center for Innovative Structures and Materials. Professor Xie was elected a fellow of the Australian Academy of Technology and Engineering in 2011. His research impacts in the field of structural optimization was recognized by the 2017 Colonies Rose Innovation Award and the 2017 AGM Mitchell Medal. In 2019, he was appointed a member of the Order of Australia for significant service to higher education and to civil engineering. In 2020, he was awarded the Victoria Prize for Science and Innovation. And in last year, 2022, he was named the Sir John Holland Civil Engineer of the Year. So Professor Xie is one of the most influential scholars in his field, with more than 500 publications and over 27,500 citations. Today, Professor Xie will give us a lecture on the topic of architectural design based on structural performance. So with no further ado, please join me and welcome Professor Xie.
Thank you, Dr. Yan, for your kind introduction. And thank you, Professor Philip Yuan, for inviting me again to deliver a lecture to the International PhD program. I think this might be my third or fourth time doing the talk in this PhD program. I'm very honored to have the opportunity to share some of the work of my research team in Melbourne and in Nanjing. The theme I'm going to discuss tonight is about a design approach based on structural performance. Okay, there are many different ways you can propose a design. The technique we have been using is purely based, or it's related to the structure behavior and how to make the structure more efficient. And while we're looking at the efficiency, we are also seeking to find some elegance in the design outcomes. The technique we have been using is based on a very simple concept. So if you want to design a better structure, we can use a method called evolutionary structure optimization, a technique proposed by my team almost 30 years ago. So the idea is to improve a structure design by removing the unnecessary or inefficient material from a current design, and gradually we will be left over with a shape which is not only lightweight but also showing some elegance. And such a concept is very easy to understand and can be easily implemented and linked with existing design tools and analysis software like Abaqus, ANSYS, Nastran, or the CAD software Rhino. I'm going to show you a very simple example to explain what is evolutionary structure optimization. Say if you want to design a structure with this given boundary condition and loading condition. So in this case, we have 1 point fixed on the top, and we have gravity load applied to the whole structure. We want to know what would be a better shape or more efficient shape to satisfy this given boundary condition and loading condition. So if we don't know the answer, it doesn't matter. We can start from this square shape as the initial design and divide it into small bits and pieces. These are called finite elements. So with this finite element mesh, we will be able to find the stress distribution and deformation of the structure very easily. So we would get this stress distribution for the initial design. If you look at this colored image, we will notice that this is the stress distribution of the structure. On the four corners, these purple colors indicate the stress is 0. So if the stress is 0, it indicates that these areas have very low efficiency. So these materials are not useful. They are only adding the weight to the structure without contributing much to the structure performance. If they're redundant, why can't we simply remove these areas? That's what the evolutionary structure optimization is about. So every step, we remove the least efficient material. So every time the material with the low stress will be removed, and gradually we will get a new shape, like an apple. And this apple shape is pure coincidence because biological material like apple or other things like trees, they grow in a very complex way. We are getting this shape because we are using a certain design criteria. In this case, we are removing the least stressed material. So in the new design, we are getting a shape with uniform stress distribution on the surface. So this is only one of many possible shapes we could get depending on the design objectives or design constraints you use. And if you use the stress level as a driving criteria, we get this shape. If we are looking for a different design object, say minimizing the vibration frequency, we could get a totally different shape. But the same concept is generally applicable. So we can use the same concept to maximize the stiffness of a structure or minimize the deflection of a building, or you can control the vibration frequency or maximize the buckling loads. We have done all these, but I'm going to show you some examples today which are closely related to architecture or structural engineering. When you're trying to find most efficient shape, it really depends what material you use. Some materials are more suitable for compression, like concrete, stone, or masonry, and other structures are more suitable for tension, such as cables, membrane, or fabric. So if you're using materials like steel cables, you want your final shape to be in tension. And to find the shape, again, you can start from initial design, any shape, then every step you remove the elements with the highest compressive stress. Because in this design case, we want to avoid compression in the structure. So the elements with the highest compressive stress will be deleted in every iteration. I'm going to show you a very simple example of tension-only structure. So if we have this structure where we have 2 points fixed, these 2 points on the top fixed, we apply a gravity. And we want to know what shape would be most suitable for if we are using a material like steel cable. So we can start from this rectangular shape, and every time we remove the material with the highest compressive stress, you will see this process. So every time the elements with the highest compressive stress will be removed, you will get a shape like this. This is called a catenary. So if you hold a steel cable, as a very heavy steel cable at the 2 ends, that shape you get would be exactly the same as this catenary curve on the screen. So, and in addition to the shape of the curve, you would notice that the structure has bigger areas on the 2 sides and a much smaller cross-section at the bottom. This is because on the 2 ends near the support, the section needs to support almost half of the weight of the whole structure. That's why you have relatively larger size here and there. At the bottom, the forces are much smaller, so you have a much smaller cross section. So through this simple process of removing material with the highest compressive stress, not only do we obtain a catenary overall shape for the structure, but also we obtain the relative cross-section area for every point of the structure. So this is how we design tension-only or predominantly tension-only structure. I use the word predominantly because for a general structure, it's not possible to obtain a design where every point is in pure tension. But we can get a design where most of the points are in tension. And we can do the opposite if we use a different material. So if we, these days, we design a lot of structures using concrete. Concrete is good for compression. So to get a compression-only structure, again, you can start from any initial design and then remove the elements with the highest tensile stress. So if you, in every iteration, you remove the elements with the highest tensile stress, you will get a new design where it's predominantly in compression. So I show you one example we did many years ago. This was in collaboration with my colleague, or my former colleague, Professor Mark Barry, who was the executive architect for this famous church in Barcelona. Many of you would know that this structure or this project was designed originally by Antoni Gaudi and almost 100 years ago. In those days, there was no computer, no evolutionary structure augmentation techniques. So what Gaudi did was using his observation of nature, and also he played with physical models like hanging chain model. One of the models was shown here. He may not have used the hanging model directly for this particular project, but he has used such models in many of his other projects. So if you look at a simpler version of a hanging chain model, so this model is actually inside this cathedral. So next time when you visit Barcelona, you will see this model in the church. In this model, every point in the chain will be in tension, and there's a mirror underneath this model. And I actually took this photo myself. If we build a structure using this upside down hanging model, every point will be in compression. So if you compare this in reversed hanging model with Gaudi's design, you will see a lot of similarities. But the reason I'm showing this example is if we use evolutionary structure optimization, we would be able to automate this process, and we can consider far more general loading cases. For example, in the hanging model, you can only consider gravity load. If you use evolutionary structure optimization method, you can consider the lateral load, such as earthquake, the wind load, and all the other loading combinations. So we can apply all the loads, and because this structure is made of stone, it's like concrete. So you want the structure to be in compression. So you can start from this initial design, that every time you remove the material in with the highest tensile stress, you will see this process. So every iteration, you remove the material with the highest tensile stress. That's a structure would be most suitable for compression, such as masonry, concrete, or stone. We did a series of research on these structure elements in the Sagrada Familia Basilica. So this is an example where we want to know the best shape for 3 columns on a slope. So we start from this initial design. So we cut a few slots to indicate that there are 3 columns, and every iteration we remove the material with the highest tensile stress, and within a few seconds, using our ESO process, we will be able to find this shape. And if you go to Barcelona next time, have a close look at the columns on the Passion facade. So these columns were designed based on some of the joints left behind by the original architect, Antoni Gaudi. And also, this was further improved by Professor McBurry through parametric design. If you compare our result with the actual column, you can see they're almost identical in their shape. This is not a coincidence. So we have used totally different techniques to arrive at these shapes. So in our case, we used computational method, generative design. In Gaudi's case, he used physical model observations, and he's a genius as well to get this shape. But our design objectives are the same. We want to create a most efficient structure shape that is most suitable for the material selected. So our design objectives are the same, but we simply use different design techniques to arrive at the same conclusion. We also did some 3D models. So these are try to design 2 columns on a flat surface. So starting from this initial design, every step we remove the material with the highest tensile stress, and then we would arrive at such some odd shape like this. It looks like tree branches. It might seem to be very strange to get this shape, but if you look at the main column inside the Sagrada Familia Church, they're almost the same. You can see these tree branches within the main columns as well. So far I have shown you the technique of gradually removing inefficient material from the structure. Actually, another common practice the engineers follow is when you have an initial design, you often, after you do the assessment, you quite often find that some parts of the structure do not satisfy some code requirement. Some corners might have very high stress. If you see this, the engineers often increase the plate thickness or add some material at these weak points. So these are the bidirectional approach in engineering practice. We have added this idea into our algorithm. So when we remove the inefficient material, we can also add material to the most needed regions at the same time. So this is a bidirectional evolutionary structure optimization, or also called BESO. If we follow such a process, the result would be far more robust and efficient. It is more robust because if you only allow material to be removed, sometimes you may get the suboptimum because optimization process is highly nonlinear. Some of the material removed in early iterations may be required. In later iterations, you may find that the material removed in early iterations was wrongly removed. It's actually needed. But if you don't allow the element to be recovered, then you can't do much. You're on the wrong track, or you're on the suboptimal track. So if you allow the material to be added, then you can actually remove a lot more material in each iteration, because even if you remove the wrong element, you can recover them later on. So that's why we call it more robust. The BESO process is more efficient because with BESO, we don't have to start from the full design. So remember that apple example. We don't have to start from the square shape. You can start from a few elements, say like a plant a seed. Let the seed grow into a large apple. So that's why the structure analysis time would be much reduced if you use a very small finite element model to start with. So the BESO method is more robust and efficient. I'm going to show you a very simple example to illustrate the BESO idea. So in this case, we want to design a bridge type of structure. The four bottom corners are simply supported, and we have a loading uniformly distributed load on the top, and we leave a gap in the middle so that the traffic would go. So this is the geometric constraint. So we need to have a gap in the middle of the bridge, and all the rest can be done by the computer. The initial design could be also very simple. So we can start from this very crude design of four straight columns with a slab. And this could also act as a bridge, but it's not very efficient. The connection between the column and the slab, at the connection, there would be stress concentration. So this bridge could break easily. And also it's not beautiful either. No one would be paying you for a fee if you propose such a design. But the computer, with the help of the computer and our BESO algorithm, it can create a far more innovative and efficient design by simply following the process of removing inefficient material and adding the material to the most needed location. I show you this process again. So we are not making small modification to the initial design. it's making huge changes. Actually, it has changed the structure concept. So from a 4-column and a slab, the BESO process has come up with an arch bridge. So this arch bridge is a different structure concept to the beam and column design. In addition to the main arch, there are additional branches like a tree branch. And so we have tree branches plus the main arch to make the whole structure to be evenly loaded. So it's structurally more sensible and more effective. The other comment I want to make is, although we are using mechanistic rules, so we only, in our computer code, we only specified the structure performance in the criteria. But surprisingly, we obtained the result we are getting is very organic and elegant as well. So we haven't specified any artistic rules or artistic intentions in the design process. But because the design outcome satisfy the structure performance very well, and in that process, we actually obtain some designs which has inherent beauty in it. When we designed ESO and BESO method, originally we were thinking about applying these techniques in aerospace and aeronautical engineering, because that's where I was working in aeronautical engineering department in the University of Sydney. Reducing weight of aircraft and rockets, they are very critical. It's very critical to have such topology optimization techniques. Such techniques are still very important. So I was in China 2 weeks ago. So I was invited to several forums to show how topology optimization techniques could be used in aerospace structures for the weight reduction and for metal 3D printing. I'm telling this long story because I was surprised that the first group of people who used our techniques in real projects were a group of Japanese architects. They find the outcomes from the ESO and BESO techniques very elegant and organic. So they started, instead of engineers in aerospace engineering, so a group of architects first used this technique. So this was done about 2004. So they modified the original ESO method and they called it extended ESO method and designed this office building in Japan. So this was constructed about 15 years ago. Oh, yeah. There's some other larger projects which use the extended ESO method. So this one was by the famous architect Arata Asazuki. And I think many of you would know that he was the Pritzker Architecture Prize winner in 2019. And he worked with the famous structural engineer Masuro Sasaki and created this beautiful structure for the Qatar Convention Center. This was built about 10 years ago. And so these are some of the photos of that project. There's another project in China by the same architect and actually same engineer as well. So both Arata Asazuki and Sasaki were involved in this project, and the shape was obtained using the extended ESO method. And my team has worked with many architects in applying the BISO technique in various projects. And I was very fortunate to work with Professor Philip Yuan as well in some of the real projects in China. I'm going to show you some of the examples we have done using the BISO technique. This one was for a footbridge in Melbourne in collaboration with Tim Black in BKK Architects. So the information we need to start the topology optimization process is very little. So we need to know the boundary conditions. This is very important. We need to know some basic information about the dimensions. With that, we would be able to find many different shapes. If you have different boundary conditions, we would obtain totally different shapes. So the design for on the top is for the case where you're building a bridge against two very solid rock faces. So the two end planes are fixed. So you can't have any horizontal movement on the left and right hand side. If your boundary conditions are different, say in the lower case, we have the left-hand side is sitting on a simple support, a pin. On the right-hand side, we have a roller. So by simply changing the boundary condition, we got a super beam like this, a totally different shape from what you obtain in the above case. So we are, as engineers, we need to be extremely careful with applying the correct boundary condition. Otherwise, you may get a pretty picture, but it's a very dangerous design. So if we use this design on the top, we put a simple support on the left, a roller on the right. This bridge would collapse immediately because there would be a huge bending moment at this point. So we need to get the boundary conditions correct before you start evolving. And we can also specify periodical conditions. So the bridge may be, say, very long, but it can divide into same modules. These are the periodic conditions. So these are some of the outcomes we got. This is a design proposal we put to the road authority in Melbourne. I think this was done in 2007. We were 20 years ahead of what the market could accept, or 15 years ahead. So at that time, the road authority in Melbourne said this kind of structure could not be built. That before those projects in Shanghai and Qatar was built. So instead, they built something like this. This is a real case. I'm not making up the story. So they rejected our proposal, and instead they built this. This is near the Marvin Station in Melbourne. We could have something like this, but because I said it cannot be built, so I asked my student to build a 1:4 scale model in the lab. So this bridge, it's periodical around a circle. So we have 6 identical pieces in a circle. So these white foams will become the holes, and the gaps we can put in the steel bars and fill in concrete. Then we can make 6 identical pieces and bolt them together. So these 6 identical pieces are connected through the bolts and nuts. So just to show that it can be done. This is also many years before 3D concrete printing become popular. So nowadays we can make this kind of structure even more easily with the 3D concrete printing. This is another similar bridge we have done. This was in 2019. My team, Nick Barr, and I did a project for architecture firm in Shanghai. So the initial design is simply a enclosed tube. Then by gradually removing the inefficient shapes, inefficient material from the tube, we'll be able to find such a beautiful design for a footbridge. This is another view of the bridge. This is another bridge proposal we did with BKK Architects. Again, the initial design is simply a circular tube, and by applying the loading and boundary conditions, we were able to find such a innovative and beautiful, and at the same time efficient design. I'm going to spend next 10 to 15 minutes discussing some of the assumptions in the conventional topology optimization. If you have read some papers about topology optimization, you would know that topology optimization is defined as a technique to find the best design of material distribution in a structure under prescribed support conditions and loading conditions within a given design domain, while satisfying various other constraints. So this is what most people believe, how topology optimization method should be done. Last year, Professor Philip Yuan asked me to contribute a paper to a new journal he was editing. The journal is called Architecture Intelligence. So I thought about this invitation for a while, and I decided to revisit all the assumptions in the conventional topology optimization. And so I'm going to show you some of the thinkings I've got from that process. So first of all, to find the best design, this has been the thought of optimization for many years. So people always want to find the unique and the global optimal solution, and all the mathematicians and theoretical scholars would always ask you, oh, you have a new optimization method. Can you guarantee your algorithm is producing the unique and the global optimal solution? And they use this criteria to determine whether your method is correct or your method is acceptable. This is like what you see in this picture. So this is the Mount Everest, the highest mountain of the Earth. You can see all these people are trying to reach the peak. This peak is a unique and a global optimum. This is like what people used to do for optimization. They want to do the iterations like this, climbing up gradually until you find the very top. But if you think about design, this does not have to be the only scenario. Some of you might have been to another place in China called Zhangjiajie. These mountains, they're not as tall as Mount Everest, these peaks, they're of similar height. Although they are not the global optimum, they're not unique, but each peak is showing a different view. You can't say they are ugly. They are offering different views from each peak. So when we do architecture design, perhaps we don't have to trying to find the only solution. We can find many different solutions to offer to your clients and to satisfy different needs for different people. So this is how, what I call, we can try to find multiple solutions from the optimization. So to achieve this, my team has been trying to develop various algorithms to create diverse and competitive designs without changing the loading and bandwidth conditions. The two key words here are diverse and competitive. Diverse means it's geometrically different. Competitive. So although we are not trying to find the global optimum, we still want every shape, every design from our process to be efficient enough. So it's not 100% as efficient as the best solution, but it might be 95%. But if it's 95% structure efficient, it is good enough for a practical design, because any practical design would have to consider many factors. Structure performance is only one of many factors we need to consider. So if you only sacrifice 5% of your structure performance, it doesn't really matter. But the advantage of doing this is you can suddenly have many different shapes to satisfy other requirements. So how do we find these multiple solutions, the diverse and competitive designs? My team actually come up with many different strategies. I'm going to show you some of the simple ones. So the simplest way to find different solutions is to change some of the parameters in the algorithm. Some of you might be familiar with coding or generative design. In any algorithm, you would have some parameters which you can change in order to fine-tune your solution or in order to change your design outcome. So one of the parameters in Bezier method is called filter radius. So I show you this simple example. Say, in this simple example, so left-hand side is fixed. We apply a point load on the right. So this is what you normally get if you apply topology optimization. But this shape is not the only solution which can efficiently support these given force and boundary conditions. We can actually find many other shapes by simply changing the parameter filter radius. If you have a larger filter radius R, then the structure components are larger. And if you use smaller R, the structure components are smaller, so you have more details and more members. So this is a very common parameter in the topology optimization technique. By simply changing this parameter, you would get many different shapes. The geometries are different, but if you look at the structure performance, the stiffness, the overall stiffness of the four designs only differs by 1.4%. So in terms of the structure performance, they're almost equal. But suddenly we have four very different shapes to satisfy many other requirements, including aesthetics or some functional restrictions. So the overall purpose is to find different shapes without reducing the structure performance. Changing the parameter is one of the simplest and most effective ways of achieving this. Another strategy or another tactic is to penalizing the existing design. I'm going to show you one example, say here. So this is So this is an example of designing a bridge. So we have these two bottom points fixed, and if we only require the structure performance, we will get this design. It looks nice. We could build this bridge somewhere, but perhaps a few months later, your client asks you to design another bridge. You can't, or you shouldn't use the same design. You shouldn't build the same bridges or copy a design from others. But it doesn't mean that you can't use topology optimization again. What you can do, you can start still using the same topology optimization process because there's an existing bridge which might have been proposed by other design firms, or it has already been built either by yourself or by others. But so you can apply some penalty to the existing design. So you say, all the material which has already appeared in this existing design should have a lower priority to survive in the next optimization process. If you do that, you get another design using exactly the same design process, but only have the existing bridge material to have slightly lower priority to survive. You can do the same. So you can design the third bridge by penalizing all the existing designs before. So in this case, we have two existing bridges, and the material that has appeared in these two existing bridges will be penalized when you do the third design. So if you do that, you will get another design. So you can keep this process again and again. You can get many different designs by penalizing all the existing design before the current round of cycle. The three bridges look quite different, but if you compare their structure performance, you will notice that the overall stiffness only differs by 3%. So in terms of structure performance, they're equally good, but we have multiple shapes to offer to your clients for them to choose from, or to satisfy other non-structural requirements or restrictions. So this is how we can obtain different designs by penalizing the existing shapes. The third tactic we have developed is to introduce some randomness into the optimization process. So I show you this very simple example of a cantilever beam. So the left-hand side is fixed. We apply a point load. On the top, that's a normal topology optimization process. And on the bottom, we dig some random holes in the initial design. So what you see is, you can see these holes. These holes are randomly dug onto the initial design. These holes can be filled later on if it's structurally important. We only have this initial host to change the evolutionary direction. So we deliberately make some defects in the initial shape. And because of these initial and temporary defects, we get a totally different shape. So the top is a normal design outcome, which symmetrical loading, symmetric boundary condition, we get a symmetrical design. But top in symmetric boundary condition, but the random hosts are not symmetrical, so we obtain a totally different design. So they look very different, but the structure performance are again almost identical. These are some 3D examples of the cantilever beam. It's on the left-hand side, it's 100% structure performance. On the right-hand side, we have introduced some random cavity into the design domain, and so we get four different. Sorry, in this case, we didn't create random cavity. We have applied some random penalty to the sensitivity of each element. So the original sensitivity is beta I. Then for every beta I multiply a random factor alpha. The original sensitivity is alpha I, and I multiply the original sensitivity by a random factor beta I. And this beta goes within the range from 0.85 to 1.15. So we choose a random number between this range to every element. So we deliberately change the importance of each element. And so when we do this, every time we will get a different shape because these factors are randomly applied to every element. So we get 4 totally different shapes, and the structure performance is only different by less than 1%. So although the shapes are totally different, but their structure performance are not affected very much. So, so far I've addressed the problem or the conventional definition of the best design. So, if we are dealing with architecture design, if you are talking with your architecture friends or your clients, most likely they would not. They're not. They would not insist about the best design. This best design is the best structure performance, but there are many other factors you need to consider. So what I'm saying here, when we try to come up with a structure design, it doesn't have to have the best structure performance. You can come up with many different designs, so diverse shapes, but all we need to have is to have these designs with high structure performance. It doesn't have to be the highest structure performance. So next, I'm going to look at the conventional assumption of under prescribed support conditions. So when we do any structure design, normally you need to specify where the supports are first. But in recent years, we have actually developed some algorithms which can find the more efficient support locations. So this is one of the research works we did during the COVID years. So in this case, we want to know where would be the most efficient column locations for a structure like this. It could be any roof, and under the roof, so there are 1,500 possible support points, and we want to find out. Say the architect may specify the number of columns in the final design. In this case, the architect specifies 7 columns, but where to put these 7 columns out of the 1,500 possible locations? It's a challenging task if you want to do it manually. If you try and error, it might take weeks to find the best locations. But we actually develop some algorithms which can find the best column locations automatically. So this thing is the final solution. C is the opposite of stiffness. If you have a smaller C, it means the deflection of the whole structure is smaller. So the final one, the optimum one is 2,700. So if you do it manually, if you allocate this column manually, you will find all the deformation is much larger. So this one looks similar to the optimum design, but still the compliance is almost twice as big as the optimum solution. So we have developed a method which can automatically find the best support columns under a flat roof. We have further developed the algorithm so we can find the best locations of support. So in this example, it's like a bridge. So we have 2 ends fixed. If you say I have 2 supports, and our algorithm will be able to find the best 2 points for the support. If you say I can have 4 supports, and the algorithm would be able to identify the best 4 points for the supports. And if you allow more supports at the bottom and on the 2 sides, again, you will be able to find the best support locations. This kind of techniques are quite useful because when you design bridges, sometimes you may not be allowed to have support at the bottom, the horizontal line, because the valley might be very deep. So you can only put the support on the 2 edges for the bridge. In that case, so we say we can only specify the candidate support point on the 2 edges. Then you wouldn't have these 4 columns. So this kind of algorithm would be quite useful for you to find the support conditions when you design bridges. And another thing which is commonly assumed is the loading condition. And in most structure design problems, you would be given where the loads are and the loading directions. But we have developed new algorithms which can find the best loading points and the best loading direction. So this is a simple example. So an L-shaped bracket, the top is fixed, and we want to know which point we should apply the load. So we can actually find the optimum location for the load. So if the load is applied here, then the overall deformation is minimal. Or if you allow the load to change direction, then the optimum location is here and in this direction, because this point is fixed. These points are fixed. So if your loading is in this direction, you can imagine the overall deformation is smaller. And this is another case where we can optimize the topology, support location, and the load location simultaneously. So here we can say there's a fixed uniform distributed load. So these loads cannot be changed, but we have 2-point load on the front surface. And the location of these 2 loads can be determined as design variables. And also the topology can be designed, and also the support locations. So in this case, we say you can have 4 support points, and the location can be determined by our algorithm. So this is what we get. In these first 2 images, we are assuming that the whole wall is fixed. On the right-hand side, we say only 4 points fixed. And using our algorithm, we'll be able to do load location, support location, and topology optimization all simultaneously. So that actually, so far we have removed restriction of the best design. We have removed the restriction of prescribed support condition and loading conditions. And let's look at the given design domain. Quite often we are restricted by the design domain, but we can use the different design domain to explore many different options. This is actually a real case study. I think Mr. Lai Yaping is in the audience today. Is a senior bridge design engineer in TY Ling International. So at that time, we were trying to find a bridge shape for a footbridge in Changsha. So we were trying to explore different forms by simply changing the design domain. So the gray area is where the design domain is. So you can put material in any location within the gray area. So if we specify different design domains, so in the second case, we say the bridge must be, all the structure must be below the deck. So there's no structure components above deck. So you will get this shape. If you say you must have you can only have circular, half circular design domain above the deck, you can get this. So by simply changing the gray area for the design domain, we come up with 4 totally different designs. And this is an example by a PhD student in Kyoto University. It's inspired by an example from Amoeba. So in this case, we say you can put material anywhere, but we can't remove or change the A. This A is the non-design domain. So no matter what change you have, this is something we have to preserve. So by fixing part of the design domain, we will be able to find a quite innovative shape. It seems A is a restraint, but this constraint actually creates some opportunity for some unusual shapes. It can also setting part of the design domain as a prohibited region. So this is actually the bridge example. So if you don't specify any prohibited region, this bridge example would produce an outcome like this. Obviously, it's not good for a bridge because underneath the deck, you can't have any traffic to go through. So in order to satisfy that functional requirement of a bridge, we have to specify geometrical constraint. That constraint is actually driving the design innovation. The two bridges, obviously with additional constraint, the structure performance is lower, but the new design satisfy the functional requirement far better. This is another piece of recent work where we can allow the design domain to change automatically. So this is a simple beam. When we apply the point load, the conventional topology optimization would produce the design outcome shown in B. But if you allow the gray area, the design domain to expand according to its needs, so we have created a process, the algorithm can automatically add blocks of the gray area so it can grow into a new shape. And this new shape, so designs in B and C, they use same amount of material. So the black area is the same in two outcome, but the overall stiffness is increased by more than 200%, because you have a much deeper beam here to resist the load. So using the same amount of material, by allowing adaptive design domain, you can create a far more efficient structure outcome. So by now, I have actually removed all the assumptions in the conventional topology of optimization. So we don't need to seek the best solution, and that is the unique and the globally optimum best design. This is not something we need to be worried about. We are more interested in finding diverse, many different solutions and the structure efficient outcomes. And the second point, we don't have to restrict the load and support conditions. If we allow the support location and load location to change, we actually create more opportunities for ourselves to find alternative structure forms to satisfy the functional requirements by reallocating the support locations or adjusting the load locations. And instead of restricted by a design domain, we should use a design domain as an opportunity to explore many different alternatives. We can create many unexpected design outcomes if you allow the design domain to change, or you want to fix part of the design domain, or if you want to prohibit part of the design domain, do not allow the material go into certain regions. So what I conclude is most of the assumptions in conventional topology optimization are unnecessary. They're imposing severe limitations on the design outcomes, and they're hindering creativity in the architecture design. So I'm actually quite very grateful to Professor Philip Yuan to invite me to write the paper. And I give this topic a very deep thought, and I wrote the paper. So if you're interested to know more details, you can go online and you can download this paper. It's open access. It's freely available. And I give the overall concept a new name called Generalized Topology Optimization for Architecture Design. So I have broken down all the limitations of traditional topology optimization and made the technique more suitable for architecture design. after this work, my team has been thinking about another important topic in the age of AI. So there's, I'm sure many of you have been either been using or testing some of the AI tools. And in our case, we want to integrate the topology optimization with the interactive. We are trying to have some interaction between the designer and the computer, so to make the optimization process more useful. So what I'm talking about interaction here. So all the examples we have shown here, the user would passively wait for the computer to produce an outcome. There's very little influence the designers can make on the optimization algorithm. So when you hit the enter box, the computer will start running, and then at the end, it will show an image on the screen. That's how it is done. But as designer, sometimes we want to have more active participation in that process. So we published this paper only yesterday. So I'm going to show you some of the latest work we have done to enable the designer to have subjective preference to be involved in the topology optimization process. The first part is, so if you look at the 4 images on the left, this could be the diverse solution from our previous work. So say if you change the filter radius or other using other techniques, we will be able to find 4 solutions. And once you got these 4 solutions, the user or the designer can put a score to each one. So if you don't like the shape of the first one, you say, oh, I give a score -3. And the second one, and it's closer to what you're trying to get. So you get -1. So the score is ranging from -5 to +5. And the 4th image is this is closer to, this is almost what I want. So you give a score like 3. After you've given a score to each of the 4 solutions, you get the computer to run it again and produce the new set of topologies. So the previous 4, these are called parent topologies, and the next set we call it child topologies. So if you have a very high negative score, you can see the new shape is quite different. And then, so by allowing the designer to give scores, then you can guide the topology optimization process to produce a design which satisfies your artistic preference. So this is using subjective scoring to influence design outcome. The next one is you can do some drawing. Say if you want to design a chair, if you use topology optimization, if you use Bezier, you will get this shape for the given support and loading conditions. But some of the designer may have some ideas. Say, I really would like a design similar to this kind of shape. This is a bit arbitrary, but this is given as an example. Say, I wish to have a design which looks similar to this, but we want to use a topology optimization technique to produce a structurally efficient. It may not be the most efficient, but it is structurally efficient. So if you do that, you will get 3 different designs. So in these 3 designs, it has considered your drawing, this sketch in the initial input, and also in the optimization process, it's also trying to make your structure as efficient as possible, and also considering your drawing. You can put some weighting to see how strongly you want your drawing to appear in your final design. If your emphasis is 100%, then the topology optimization can't do anything. It just produce what you have shown. If your weighting is smaller, say 50%, then it will consider the weighting of 50% of your drawing, and the other 50% is used for the topology optimization algorithm, and you can get something, a compromise solution between your drawing and the topology optimization. So I show you a simple video of how this is done. So you run the topology optimization, you get 4 solutions, you give the score, then it will use the score to produce some of the design. Here you draw top, and your design outcome would have top. Not exactly, it's somewhere between your drawing and the topology optimization. And this software is available online, so you can download this software freely from the internet. If you can't find it, just send me an email. I can send you the link, so you can play with this if you want. I'm going to I'm going to spend another 10 or 15 minutes. Then my colleague, Dr. Nick Bao, will take over to show you some of the results of the recent workshops using Amoeba software for topology optimization. So here I'm going to show you a research project we have done with Arup and Lead. I'm trying to design all the connections. These are the nodes. So if we do the structure analysis, we will be able to find the forces in each member and moments in each member. And using that input, we will be able to design each connection to make it lightweight and also make it elegant. So this is one of the nodes we have produced. So this member is fixed. We have 2 shear forces, and this is a lightweight connection we obtained. Not only it's structure efficient, it's very beautiful as well as a design. So these days with 3D printing technology, we will be able to print the metal connections like this. So this is a stainless steel printing, and we have actually using metal printing and printed quite a few components designed using our BISO technique. But using direct metal 3D printing, there's 2 concerns a lot of engineers would have. One is it's very expensive to use this metal powder. You melt this metal powder into this large metal component. The other is possible defects in these 3D printed nodes. If you are load bearing, then you need to make sure there's no defects inside. So an alternative way to the direct 3D metal printing is to print the wax model, because printing wax is far cheaper than direct metal printing. Once you get the wax model, you can dip this wax model into ceramic slurry to create this ceramic shell. You can melt the wax inside and then use this ceramic shell to cast a node. So this is how we cast a node. So in this photo, we actually used BISO to obtain the shape. So we use a topology optimization to obtain the shape. Then we use a 3D printing technology to print the wax model, and then we created the ceramic shell. Then the last step is using the traditional casting technique to produce these very nice cast node. So compared to the direct 3D metal printing, the cast node is much cheaper, and also it's a component which can be used in engineering applications straight away, because casting is a technique which has been used for many, many years. We have standard design codes to follow. And recently we have been collaborating with Mr. Lei Yaping from TY Lin International to design several large-scale bridges in Chongqing. So in this case, the main span is 350 meters. And the key technology used here is a multi-material BISO method. So we can, using the multi-material BISO method, we can automatically place the steel cables in the tension region. So these thin members on the top are made of steel, and the bigger white members underneath the deck, these are made of concrete. Our multi-material BISO algorithm can automatically find the right material in the right region and to produce such a spectacular bridge design. And so this is a BISO process. Again, we explore different design domains. This pink area is a design domain. So eventually we required, for the purpose of construction, we require the bridge to be symmetrical on the two sides, so it can be more balanced when we construct this bridge. This is another bridge we designed with Mr. Lei Yaping's team. And so here we use BISO in two aspects. One is the wind bracing. So these crosses to resist the wind is obtained through the BISO process. So you start from this gray design area, and then through BISO process, we will be able to find these crosses and then obtain this overall shape. The other aspect of design optimization is we applied the BISO technique to the four spherical joints at the end of the arches. And these joints, these spherical joints are extremely important, and they are heavy. I think it's each joint is around 71 tons. So the four joints would be more than 300 tons. And we applied the topology optimization method to reduce the weight of the four spherical joints. We were able to significantly reduce the weight. And I think this joint would be made of cast steel. And we should be able to save a lot of weight from these four spherical connections. And I'm going to show you the software we have developed purely based on the BISO technique developed by our team. So the BISO software is developed by my team in China. They're based in Nanjing, and when we developed this tool, we were keeping our architect students and collaborators in mind. So we choose Rhino Grasshopper as a platform. So Amoeba is a plugin to Grasshopper, and all our computations are on the cloud. So Amoeba can be a lot of students can learn Amoeba very quickly, and Dr. Nick Ball will show you some of the outcome from the workshops. Normally, the student can spend one day to learn how Amoeba works, and the next day they will be able to use the software to design many different things. So I'm showing you some of the examples from the students. This chair. It's a real chair. When you come to my office, or if you go to Amoeba company in Nanjing, you will see this chair. We won some prize in a competition in Xi'an 3 years ago. 2 female students used Amoeba to design these high heel shoes and 3D printed. And this is a project Dr. Nick Bao and his team designed and constructed, I think 2 years ago. Nick Bao will give you more detail. This is 4.5 meters tall. It was the shape was obtained using Amoeba, and then it was constructed using high performance concrete. This is another student work. They redesigned the Eiffel Tower. Considering this original structure was designed and built more than 100 years ago, with a modern design technology and additive manufacturing, perhaps the shape and could be totally different if we want to take advantage of the new technologies. This is another example by an undergraduate student. He's now a master student in Nanjing. I think he might be in the audience. He's a very clever student. And so finally, I'm going to show you a short video about Amoeba. So by now you would understand the whole concept of BSO method is very simple. So all you need to do is to gradually remove the redundant material and adding material to the critical location. By using this simple idea, you will be able to find very efficient, very elegant, and organic design outcomes. And with Amoeba, it also has a function of smooth the mesh and reconstruct the model after the topology optimization. And we can specify non-design domain and produce multiple options. So I'm able to show you all these interesting examples. It's because I have a very talented team and I have many supporters.
I'm very honored to be here to give you the second part of the lecture about the architecture design based on the structural performance. So I'm Nick Bao. I'm a lecturer at the School of Architecture and Urban Design, and also research member at the CISM, leader by Professor Mike Xie, and also partner of Amoeba. I'm a registered architect. So the topic I'm going to talk about is architecture design based on structural performance, and the detail layer is a structural performance driving generative design and robotic 3D printing fabrication. So start from the precedent, the Gaudi's, the Gothic building and the Gaudi's church, and nowadays the Smart Slab and the ICD's pavilion. So you can see the most of the design is inspired by the nature. So it's like Professor Mike Xie talk about how to balance the aesthetics and the structural performance. So the form is from the nature, and we are trying to make the nature form more rationally. So I'm not going to show this video too much because Professor Xie has already did. And yeah, 1990s, Professor Mike Xie proposed the BESO method. So we use this method to attend the several competition and win the first prize. You can see the material is reduced slowly, and also still keep the same structural performance, which Professor Mike Xie already introduced. And most of the typology optimization object is small scale and using the adaptive manufacture to produce. And nowadays, more architects start to using this method, a similar method or the typology optimization method in architecture design, and to create some interesting architectural form and the space. So that's why Professor Mike Xie's team developed the Amoeba software. I'm not going to show this again. This software is quite intelligent for the designer can play with, and also I will introduce some functions of the Amoeba and the result from our workshop. So also collaborate with the MIT Architecture Robotic Lab, and we were using the large-scale 3D printing robot to print some elements, including the clay, concrete, polymer, and wire metal print. So that's all I will introduce for the digital design using Amoeba and BESO, and later on the adaptive manufacture robotic fabrication. Start from the project. So the XForm 1.0 is the first project we deliver in the Digital Future 2019. So start is from the modified BESO method, which is oriented to the architecture design. It's like what Professor Mike Xie talked about. We want to use it more design driving or can be suitable for the designer and creating the more diversity of the design. So you can see the multiple design results after we input some designers' design intention to creating some openings in on the surface, on the facade, and on the structures. So the first project is start from the tree systems, which is the tree branch, and we added the load on the top of the surface and also fix the bottom point and run the BESO method using the Amoeba. And finally, we got this tree branch geometries. So you can see from this image is the process of the optimization process. So firstly, we're using the small 3D printing to testing the 3D prints. And you can see the left side is the small scale 3D printer results, and the right side is the large scale 3D printer results. So we're using the MIT robotic 3D printing to fabricate this one part of the column. So each column takes 16 hours to produce. After we 3D printing each column, then we do some modification on we do some work on the surface and then remove the streams between the branches and design the top joint and the base joint. Then we deliver into Tongji University, which before covered. And we instruct students to how to assemble it. So we only spent few hours to assemble the pavilion, which is 2 meters high and 1 point by 1 meter wide. So this first version we deliver physically. The second one is the XFOAM 2.0, which is the advanced version of the FOAMx Pavilion. So it's quite different from the XFOAM 0.1. And we divide it into the 4 pieces. And so each piece have the straight curved surface. So we fix the bottom points, then add the loading on the top. Then we run the BSO algorithm using the Amoeba and to start reduce the materials. So the final result is saving 52% of the material after we got the simulated model, a quarter of the model. So the right side is 4 meter by 2.1 by 1.5. And the full model is the right side, 4 by 4.2 by 3. And after we're testing the structural performance, so the new structure of the pavilion meets the actual structural requirements. Compared with these two pavilions, you can see the XFOAM 1.0 have 1 top and XFOAM 2.0 have straight curved top. So it's more advanced and compared with the interior looking and also the side view. So the XFOAM 2.0 have a lot of improvements. So we also print a small scale 3D printing model for the prototyping and divide the large piece into the 24 pieces using the robot to 3D printing each part. And also we deliver it to Barcelona ISS conference for the ISS Expo. And we only use a few hours to assemble on site. So which is very quick assemble methods. Also, because of we carry this model by ourselves, so we'll only bring a quarter of the model to the site. The next project I want to introduce is Intelligent Foam, which Professor Xu already introduced. Is a dictionary interior wall for the Digital Future Workshop in 2021. So we set up this 2-inch curved wall and also set up the boundary condition and adding some loads. Then start to running the algorithm to creating the future walls and the patterns on these 2 surfaces. Then remodeling the overall form and 3D printing a small scale model and testing using the FEM model to test the structural performance. And then later on, we're thinking about the new design and how to realize this new design. So collaborate with the Chinese science and construction company. Then we 3D printing the mold using the PETG material. And firstly, divide the mold into the different pieces and 3D printing each pieces, then assemble the mold. Then this is mold design. So the left one is the middle part, the right one is the 2 side parts. So we're using the new techniques to spray the UHPC concrete on the surface. So you can see the workers help us to spray the spray the UHPC, which is high performance concrete on the surface on the mold. So this is the first layer. So first layer is just normal concrete, it's not UHPC concrete because we want to keep the surface smoothly. Then this is the final layer. Final layer is manually using the brush to get the bubble out of the concrete. So after demolding, then we do some smoothing on the surface. So this is the middle part. So after demolding, there's a middle part. Then we deliver these 3 pieces of the model to the Tongji University to attending the Digital Future 2021. So the Digital Future 2021 is the half online, half in person. So the student help us to assemble these 3 pieces on site. So these are quite heavy panels, which is each panel is like 200 kilogram to 300 kilograms. So we also ask some builders to help us on site. So very heavy pieces, and we use very simple connection to join these 3 pieces. So this is the final outcome, and the video is sent by some students on site. So you can see there's the one behind the model, because we just finished the concrete very quickly within a short time. So the concrete the time for curing the concrete is about 28 days. So that's why we still keep the one supporting behind it. So after 30 days, then we remove the one behind it. So it's some photography from some students. Except this several project, I want to introduce some teaching outcome related to the amoeba and topology optimization on the architecture design, which including my teaching at MIT University, and also the Digital Future workshops, and the Cadular workshop as well. So the student from my design studio at MIT a few years ago, they're using the amoeba to generate the space for the museum, for the mountain museum. So you can see the original base structure form is very heavy, then apply some loading and supporting, and then reduce the material and still keep some interesting space. Then after that, they're using the Swan Intelligence to working on the surface to generate the more intricate forms. And some students also fabricate using the small 3D printing to fabricate some prototypes, which is from bachelor students. Then we run the amoeba topology optimization workshop XForm, which is the same name with our projects, in 2019, which is 4 years ago. So this is a very interesting design by one student, Dingming Wang. He designed a Chinese heritage building using the topology optimization plus with the timber structures. And in 2020, everything moved online. So we deliver the workshop from purely online. So the student also deliver some very excellent project. Professor Xu already introduced. This is by team Zhe Wang and Chen Yangliu and Zhuo Yuanfen. They designed the Eiffel Tower 4.0 using the topology optimization method to design each pieces. They're assembling all the pieces, make a whole Eiffel Tower. Then later we help them to 3D printing the models from Amoeba company. And also there's a few interesting design from my Cadular workshop 2020. So Dr. Xin Yan and myself, we lead a workshop which called Reform on the facade of the Gaudí's church, and then to apply the loadings and to reduce the material to regenerate the facade of the La Sagrada Familia church. And also one talented student who's from AA also working on a staircase, was using the amoeba and the topology optimization method to generate the nature-inspired staircase, which is very interesting design. So move to the Digital Future 2021. We have a very we have more interesting project and outcome delivered. So the first one is the bridge. So because the original architecture design application on using the amoeba is the starts from the bridge design. So the students get some inspiration and to redesign the bridge using the BSO and amoeba method. And another group of students to design the freeform shell building which later they make it into the architecture design, and the more interesting and the porous space becoming the gallery space, which they call the sand gallery. And finally, they're using the very interesting render to show the final outcome and application in the near the beach environment. And another group of the talented students, they're using the Amoeba and the BESO to creating the circular form, which is they using it for the Fairway project. So this is their final outcome of the project, and which is the render which they're showing in the theme park. And finally, we help them to 3D printing the geometry, the final design, which is very interesting integration with the topology optimization methods with 3D printing. And this project is designed by two bachelor students, Shu Yishen and Chen Biduan. They are very talented using the BESO methods and Amoeba to redesign the Chinese heritage building and the components, which called Dougong. And using the Zoom parts, which is to redesign the part of the components that finally for assembly, and based on the logic of the force and the loading. And finally, they Photoshop and apply on the traditional building, which is for the support of the original Chinese heritage. So there's few renders. And another group of students, they redo and reform the flying buttress, which is the another heritage building facade. They run the BESO method to creating the interesting facade design for another heritage building, Western heritage buildings. So this is final design and the renders. And another group of students from Egypt, they also design an interesting pavilion for the using the Amoeba and topology optimization. Very interesting design. And later on, they added this into their university using a render method, and making a integration with the green space and the green building with the optimize the structures. And last year, we run a new a workshop called Reforming in 2022. So with the Professor Mike Xie, Dr. Xin Yan, and Dr. Cho Wei, and Dr. Jianan Pen, due to the due to the COVID again, so we moved our workshop to the Amoeba company in Nanjing. So there's a space we deliver the workshops. So the whole team and student with some staff and some teaching assistants in the company. Then we're teaching online, so we collaborate quite well. And so this is the few lectures delivered by Professor Xie, myself, and Dr. Xin Yan, and Dr. Cho Wei's team. Then later, after student design, very interesting project, we also helped them to 3D printing using our facility to do the 3D printing, the final outcomes. So now I'm going to introduce a few projects from the students. So the first project I want to introduce is the optimize the slab, which is inspired by the smart slab from ETH. So the student also put the loading underneath and put the boundary condition underneath and put the loading on the surface of the slabs, creating the multiple version of the slab. So it's quite interesting design using the topology optimization method and Amoeba to creating the intricate columns with the slab, which is making to the one piece. And so students learn Amoeba only using 3 days. Then they start to produce the project, the works from the third day. So it's very quick. They are quite very quick learner and also very good designer to produce and deliver the final outcome. So with the another version of the smart lab and the glass curtain wall system of the library design. So then we're using the 3D printing to realize their projects. Another group of the students design a suitcase from this very regular and very heavy form. So they apply the loadings on the analysis how the suitcase the loading come from, and apply the loadings, apply the also set up the boundaries and the supportings, then start to optimize the material to make the suitcase more lightweight, and also apply the lighting, apply the systems, automatic systems, to try to make the suitcase lightweight and also have sense of the beauty. So this is some details of the suitcase. There's a 3D printing version for their suitcase. And another group of students combined with the CFD method and with the BESO method. So they analyze the wind loads from the some area, and give some do some analysis, give some information, data information from the nature, and apply the wind load on this interesting geometry, which they called it tempo, and apply the multi-agent systems, which is I told it also at MIT for the integrate with multi-agent system with the topology optimization methods to creating this intricate tempo structure and tempo buildings. And the final design is touching on the mountain, which is like a iconic on the some country area. And this group of the students also using their own method to design the project using the approach optimization. They design each panels, which is for the facade design, and each panel have different loading conditions, boundary conditions, and the loading, which is creating the panels of the facade. So you can see they creating the different type of the facade. And the different layer of the facade, and apply on the high-rise buildings. Then we help them to 3D printing this complex high-rise building prototypes, which is another version or the future of the high-rise facade design. And again, the students, the bachelor student Zhou Yuanfen, also creating another version of the bridge, which is very interesting design from he also as a teaching assistant for the Digital Future 2022 in our workshop, and also help us teaching with the student and produce his own design, which is interesting bridge design for the workshop. So another group of students, Duan Chenbi and Shen Shuyi, they design another chair, optimize the chair, which using the BESO and analysis, also getting data from the loading on the chair surface, apply the BESO method, and to reduce the material, to creating the more porous and holes on the chair. Then finally to create this interesting interesting timber chair, and there's some few renders. Then finally we help them to deliver 3D printing outcome. So the workshop is half online and half in person in Nanjing, which is I think it will be the final workshop online. Then we also invite a few guests to help us to do the critique for the final presentation. And this year, we also got an invitation from Professor Xie and Dr. Chao Yan. We're gonna deliver Digital Future 2023 in-person summer workshop. So we're looking forward to the application if you are interested in to attend. So I want to introduce something new from my research. So except the BESO method, my research also part of my PhD study, I integrate with the Swan intelligence. So which is the BESO method is developed by Professor Mike Xie and the Swan intelligence idea from my second supervisor, Roland Snooks. Then I work with Dr. Xin Yan on the Swan BESO. So from the logic, from the theory of the combine the two interesting algorithm together to do the integrating digital design, and using to develop two methods to deliver the project. The first one is the Swan BESO, is the Michael way to develop a new algorithm. The another way is the new optimized design using the agent bodies, and then use the 3D printing robotic fabrication to deliver the several projects to prove the design method or the integrated method. So the BESO method becoming the Swan BESO method, which is multi-agent based typology optimization. So Professor Mike Xie's team always deliver different versions of a BESO to get more diversity of the final results, which is suitable for more designers. So this is some algorithm development based on the Python platform. So this is the 2D version of the cantilever, which using the Swan BESO algorithm. Then after we add some Swan rules setting using the separation, alignment, and cohesion, so we can get the more interesting final outcome and the more diverse results. And this is the best final outcome. So you can compare with our testing on the long beam and on the long beam. So the normal results is on the blue image, and the BESO, by the BESO result, then our Swan BESO can achieve the structural performance and a more complex and beautiful form, which is we can sacrifice some structural performance but achieve some interesting and more intricate design. As a designer, we will need to balance the structural performance and architecture aesthetics. Then we develop into a 3D version of the design and testing in the 3D cantilever, and also using the different boundary condition and load to test it. So this is 3D version of the Swan BESO Swan BESO outcome. So you can see we're creating some lattice structures. So the development of the algorithm development is already published, so you can have a look from our paper. So we want to use the Swan BESO idea to creating the lattice structure, which is using the different method a different fabrication method to produce the final outcome. Because I believe that all the interesting design can be fabricated, which will be more useful and functional. As an architect or the designer. So the first one I want to introduce is the cast body, which is the lattice structure. We use this one to exhibit in to attend the Venus Biennalia using the lattice structure. Also combined with the 3D printing modes, then cast concrete. So there's a final outcome with the sacrificial formwork and the concrete, and this version is to remove the formwork, only purely concrete. Then also recently developed with MIT Architecture Robotic Lab to creating the metal printing components for the lattice structure. So maybe you wonder how this lattice structure can be applied. So we using our design studio to apply this multi this lattice structure to be maybe a complex architecture design facade or the interior diagonal wall. So so it can be a potential to be architecture application. Also collaborate with Professor Yuan's team in 2021 for visiting. We invite Professor Philip Yuan as a visiting professor and doing a traveling study in Shanghai and collaborate with the Archi Union and Fabric Unit's team to deliver a 3D printing concrete pavilion. So this is the pavilion combined with the Massoon's algorithm for the form finding with the Amoeba algorithm together. So to creating this optimized structure for the 3D printing concrete. So this is a final outcome and the models. Then this is a final pavilion design using the two algorithms, including Amoeba and the topology optimization. So also do some force analysis testing because the performance of the concrete doesn't have only have the compression system. So we use the reinforcements, rebar, and the steel for the tension function in the model. So you can see we added some steel reinforcement the steel bar, and in the pavilion design, and collaborate with the FU robots to deliver the project. We split the project into 18 pieces. So this is the final outcome and the video to showing how we fabricate the final projects, which is sliding the different components using the robot to print, the 3D concrete components. So due to the limitation of, because the 3D printing always have the hollow empty in the middle, so that's why we using the steel plate to apply for the fixing the steel rebar systems. So you can see we print few layers, then added a section of the steel plate, and which can help with install the steel bars. So this is a design process. This is a fabrication process. So after that, then Professor Philip Yuan's team also assemble with our students on site for the final pavilion. So this is a final outcome of the design. Also, last year, 2022, in the Melbourne Design Week, I worked with Dr. Dan Luo from University of Queensland to design and fabricate this fiber weaving tectonic projects. So the original design is generated by the Amoeba and topology optimization to reduce the material, and to keep the pavilion have a very limited material and still keep the same structural performance. And later on, using the robots from the University of Queensland, and we set up the automation systems for the weaving techniques to weave to using the carbon fiber carbon fiber weaving system and techniques to fabricate each channel of the pavilion components. Maybe I just quickly to jump to. So after we fabricate each unit, so you can see each C-sharp unit is fabricated by the robots. So we bring it to the site to attending the Melbourne Design Week. So the student with us to assemble the each unit. Then we design how to connecting each unit, and we just spend 10 hours on site to finally to assembling the projects. So the project is very lightweight, and also the elegant have a very interesting space underneath. So there's some photograph from the from on site, and we also design a small table underneath. So recently, my research also moved to the artificial Taihu stone and the marine coral design, which combined with the CFD method, which is computational fluid dynamics with the topology optimization. So the outcome is very interesting as well to optimize the artificial stone and the coral reef. So this is the final outcome for Taihu stone. We also publish a paper in the Digital Future Conference. So this is the design process, how the CFD and the water loading can apply on the surface of the Taihu stone, to creating the interesting space, to creating the interesting surface and porous space for architecture design, for architecture interior space. Then another research is start from with our students, Shen Shuyi and Duan Chengbi, to design a new Dougong. So the new Dougong with the Chinese architecture, which is Chinese traditional craftsmanship, integrate with the BESO and Amoeba. So the analysis, the assembling methods and the craftsmanship of the Dougong fabrication methods, then to use the Amoeba and the topology optimization to optimize the different geometry and different parts of the Dougong system. Finally, to assemble the Dougong system to achieve a new system and a new craftsmanship with the topology optimization method using the wooden joint. So the related paper already published in the Hybrid Intelligence Conference, and also a new extended journal will be published soon on the Architecture Intelligence journal, edited by Professor Philip Yuan. So that's all the project I want to introduce. And if you have any questions, you can also add me and also follow the Instagram if you're overseas, and also visit CISM Lab and Amoeba website. If you want to learn the Amoeba by yourself, we have a very interesting video and a tutorial in Bilibili if you're in China, and also the YouTube channel. There's a very detailed tutorial for the Amoeba learning. And thanks.
Well, thank you, Professor Xie and Nick, for the really inspiring lecture showing us structural performance could become a formal repertoire for architects to take on and to interact with. So we have a lot of PhD candidates here tonight. So I would like to ask if you have any questions. You may turn on your microphone and ask Professor Xie and also Nick. Is there any questions from the floor? Okay, there's one question in the chat. So thank you, Professor Xie, for the fantastic lecture. I would like to ask a question. In your lecture, you mentioned the Kota National Convention Center designed by Isozaki. The huge structure is very impressive, and the shape of this structure is the result of BESO optimization. However, when this structure is built, the interior is steel structure. So this huge structure is a kind of hollow shape. So this is some kind of inconsistency between the optimized shape and the building construction. So how do you think about this kind of inconsistency? Thank you.
This is a very good question. When you use the tool like topology optimization, you only use it to get a general concept. You don't have to build the obtained shape religiously. So whether it's going to be hollow or solid, but I don't think it matters that much. You only use such a tool to give you an idea of the general shape. When you implement the topology optimization outcome, you always need to make some simplification or modification in order to realize that design. It's not possible to build a solid structure so massive. So the fact that they did a hollow structure with simplified steel cages, that's because they have to make consideration of the practicality in order to make it a reality. So the inconsistency, I don't think it's a problem. It's actually involves a lot of creativity from the parts of the engineers in order to realize a dream from the architect.
Thank you. Is there any other questions? I think you may have the permission to unmute yourself. If you want to ask, you can turn on your microphone directly.
While we are waiting for questions, I left my WeChat and Instagram numbers in the chat box. So and also my email address. So if you have any questions in the future, you're most welcome to either contact me or Nick.
Okay, here's another question from Li Yu. Do you have any suggestions for beginners how to learn topological optimization? The question is to both Professor Xie and also to Nick.
Maybe I start first. There are many books and papers you can read. You can go to our website to see some of the publications, and especially the paper I showed today in Professor Philip Yuan's journal. It's called Generalized Topology Optimization for Architecture Design. That paper actually provide a list of references for you to look into. So you can read the paper to get a general idea, and then if you want to know more, you can read the listed reference there. And Nick, you may have some other suggestions.
Actually, most of students from a designer background attending our workshop, they don't have the knowledge for the topology optimization, but easily they can start using the Amoeba software, because the logic of the topology optimization, also the BESO method developed by Professor Max Xie is very easy to understand. Also, yeah, like what Professor Max Xie told, you can read some book from our website and to learn some very basic knowledge of the topology optimization and the BESO. Then quickly using the Amoeba to testing your ideas will be very easy. And also you can ask me and also Professor Max Xie and join the Amoeba WeChat group, which is not just the Amoeba WeChat group. Is we discussed a lot of topology optimization topic in the group. If you have any questions, you can also ask us in the group.
Okay. We have two more questions. One is quite technical. What are the bonding materials for the components of prefabricated plastic or concrete structures? Will it affect structural performance?
Nick, maybe you can answer.
Nick, you are muted.
Yes, when we design the pavilion and the structures, we always input the material properties when we run the BESO, and we're using the Amoeba software. So it will affect a little bit structural performance, but not overall. So so I think as yeah, because when we design the pavilion and using the topology optimization method, we design the whole geometry. But after you make the components and the prefabricate the components for the whole design, for the whole project, it might have some little impact for the structural performance. But after we're testing, it didn't affect a lot.
Okay, I think given the time, we just take a last question. So in the lecture, the mentioned structural morphology contains of 4 aspects: form, structure, materials, and force. And as mentioned in this lecture, a good design result is not necessarily 100% structure oriented, but maybe the optimal solution obtained by combining other parameters. So may I ask what the specific ways or adjustable parameters to define or to adjust the weight of these parameters in real projects?
Maybe I try to answer this. When we consider multiple factors, multiple constraints, yes, we do put a weighting on different objectives, and these weights would range from 0 to 1, and it really depends on what your design objectives. If you are very concerned about structure performance, the weight for structure performance would be close to 1. If the artistic intention is what you are focused on, so you perhaps you put higher weight for that subjective preference. So there's no definite answer to your question. It really depends on what you wish to obtain. So you play with the weighting and explore different values to see what you get. So it's not a very scientific. It's an artistic way of exploring different outcomes and make a judgment.
Okay, I think we are just about in time. So I want to thank you again, Professor Xie and Nick, to give the fantastic lecture. And I'm really looking forward to your workshops this summer. Maybe we can also see you again in Shanghai this year. Very looking forward, and thank you again.
We also have a conference in Melbourne in mid-July. So if you're interested,
yes,
you can come over. I put the website as well in the chat box before we close. So it's
yes, the IASS 2023.
Yes, so we're expecting 500 people at the conference. So you're most welcome to join us in the lovely city of Melbourne.
Thank you. Okay.
Thanks for the message from friends in Nanjing. Yeah, I look forward to meeting you as well in Nanjing. Okay, bye
Okay.
for now.
Okay. Yeah.
Thank you.
Okay. Thank you. Thank you, Nick. And thank you, Professor Xin. Bye bye.
Bye.